All right, hello everyone. Today we are going to start our first tutorial about FMCW radars and how we are going to collect data with Texas Instruments automotive radars. I don't know if we can get to the data collection part today, but I'll try to make it there so we can get started. All right, the first concept that we need to learn is the radar pulses, what radar transmits. So in this frequency modulated continuous wave radars, or that we call FMCW radars, they transmit pulses whose frequency increases over time, and they are sinusoidal waves. Uh, like their kind of transmitted pulses look like this. Its frequency is increasing over time during one pulse, and amplitude stays the same. And T here is the time. And we also call this pulses a chirp. It's basically a sinusoid whose frequency increases linearly with time, as we show in the plot here. And since its frequency is increasing over time, when we plot time versus frequency, we can see this kind of slope in the center frequency of the transmitted signal. And this center frequency is usually represented with FC. And a chirp is characterized by a start frequency FC and the bandwidth. Bandwidth is like what's your frequency difference between starting of a chirp and the ending of a chirp. So here in this case, it starts at 77 gigahertz and it increases up to 81 gigahertz. So the bandwidth becomes 4 gigahertz. And the slope of the chirp defines the rate at which the chirp ramps up in time. And in this example, the chirp is sweeping a bandwidth of 4 gigahertz in 40 milliseconds. And this 40 millisecond is the chirp duration, TC, and which corresponds to a slope of 100 megahertz divided by microsecond. And after transmitting one chirp, we keep transmitting these chirps again and again. And these chirps kind of like are being consecutively transmitted. And after a certain duration, we take these chirps and we process them. And this interval is called like coherent processing interval. It's also called a chirp frame. So usually we might have 128 or 256 chirps in a frame. So for example, if we have 40 milliseconds of chirp time, and then let's say we are transmitting a certain number of them, after adding up all of these chirp times, we get our kind of frame duration. And depending on our frame duration, we will have our frames per second in the radar data. And we'll see those a bit later. So let's look into this chirp in a bit detail. So this red plot here is the chirp, basically, where x-axis is time and y-axis is the frequency. As you can see, the ramp is increasing and then decreasing. So since this is like the ideal scenario, but in a real hardware, this ramp up and ramp going down is not like being instantly. So there's some there's some time that we need to allocate for radar to kind of like reduce down its frequency, and we allocate this time as the idle time, where we kind of like allow radar's center frequency to go back to its kind of like original starting frequency. And before like after starting sending these pulses, we need to collect these samples as well. So these samples are being collected by the receiving antenna, and we need to sample this chirp because it's a continuous signal, and in the computers we cannot store continuous signals. We need to like digitize it so that we can use it in our analysis. And here we use an analog to digital converter. So we have an ADC start time here. So this is where the ADC starts sampling the chirp. For example, this thick part in this chirp is where the kind of ADC sampling window is. So on this slope, we will take certain number of pulses. So for example, in our implementations, we usually take 256 samples from this interval, and it becomes our ADC samples, we call. And in our processing, we also call them test time samples because they are all in the same chirp. Okay. And this chirp cycle time is kind of basically your ADC ramp up and ramp down time. It's like the whole duration from chirp to chirp. And yeah, this is basically it. Do you have any questions so far? Okay, now we can move on. So basically, this is one chirp, and we are, as we said, transmitting multiple of these chirps in a frame. And for example, in this case, if you look at here, we have chirp 1, chirp 2, chirp 3, chirp 4. These chirps has kind of like, they have their own properties. For example, like their bandwidth, their ADC sampling rate, their kind of like ramp up, ramp down times, whatever it is. You can define each chirp individually if you wish, or you can use one chirp profile and use it for all the chirps. So here basically we are sending n chirps in a frame, and after a frame we have some idle time here. So this time is called interframe time, and this time interval is usually being used for processing data. Like all the chirps that we collect here are being processed in this time interval, and then we start transmitting the next chirp sequences for the next frame period. And now we'll see radar antenna structure a little bit, like what we have in our lab. So we have a few different radar platforms. One of them has 2 transmitters and 4 receivers. One of them has 3 transmitters and 4 receivers. I'll basically try to kind of describe you how these antennas work. So basically here, these 2 antennas transmit electromagnetic waves. And when there is object somewhere in the field of view of the radar, these objects kind of backscatter the electromagnetic waves, and these waves kind of hit these receiving antennas, and these receiving antennas are collecting the like frequency, amplitude, and phase of the kind of received data. And we are kind of analyzing this received data to kind of infer the range, velocity, and angle information of the targets. So in order to to be able to measure the angle, we need at least 2 antennas or 2 transmitters. Because if we have only one transmitter and 1 receiver, let's say if we measure the target as being 1 meter away from the receiver, it can be 1 meter here or 1 meter here or 1 meter here. It can be in anywhere in 1 meter distance. But if we have two of these antennas, then in that case, by the way, you can see my cursor, right? Yeah. Okay. So if you have 2 of these antennas, then what we can do from the flight time of the backscatter signals, when, for example, let's say there's a target here, okay? It reflects a signal, and it should first hit this antenna and just a little bit later this antenna, because this one is a little bit further away. And by using that kind of like flight time difference, we can kind of extract the angle information of the target, like where it's located. Now, in our radar platforms, we have uh, two transmitters and four receivers. Now, the angle resolution that you have in your radar platform is kind of proportional to your number of receiving antennas you have in your radar system, like how many channels you have. And here it looks like we have four receiving antennas, but actually we can make it act like eight antennas because we have two receivers. So how it works, if you look at the distance between these two transmitters, it's 4D. So this D is kind of uh, calculated as lambda. Lambda is kind of like speed of light divided by your center frequency. This D is kind of lambda divided by 2. So there is certain calculation for how this is being calculated, but it's something that we are going to see a bit later, probably not today. So this distance is 40, you can think of it as like a constant distance. And the distance between each receiving element is D. So from the first antenna to last antenna, we have 3D distance. Okay. So now, when we have two transmitters, what we can do? We can first transmit with the first transmitter, right? So let's say there's a target here. We transmitted one pulse with this, and it kind of like reflected back from the target, and it hits all the receivers one by one. And in the next pulse, we can transmit with this antenna, and when this antenna kind of when the like waves are being reflected from this antenna, they are again being kind of received by this like four receiving antennas, but it will act like, since there's 4D distance, it will act like these four uh, four receivers are kind of located in the right side of these four receiving antennas, and it will look like this. So basically, these first four of them are kind of the channels that are coming from the first transmitter, and the other four channels are coming from the second transmitting antenna. Okay. Now, this is something that we can do, and for the other platform, we have three transmitting antennas and four receiving antennas. And again, we have 4D distance between these two elements. But we also have another antenna in the elevation part with D distance. Okay. So now in the elevation, we don't need 4D distance because there is only one channel in the elevation. If you look at the structure of the receiving antenna array, they are all located in the same elevation position, right? So we don't really need 4D distance. But for the azimuth, for the azimuth distance, we have like four elements. That's why we need 4D distance. So now, if you think of the like virtual array, so by virtual array I mean something like this. So, for example, this is our hardware. In our hardware, we have two transmitting antennas and four receiving antennas. But using these two transmitter and four receivers, we can create a virtual array with one transmitter and eight receivers. So this is called virtual array. Your virtual arrays, virtual channels. Okay. Now, in this case, when we have three transmitters, for the first transmitter here, actually these are kind of ordered like 1, 2, 3. It's like this from left to right. So if we consider this one as the second transmitter, this one will kind of have the first virtual array in the elevation part here. And the second, sorry, this one is the first transmitter. The first transmitter is going to have its virtual channels in the down position and in this position. And but if you look at the distances, they are consistent. For example, they have 2D horizontal distance between first and the second transmitter, and in the virtual array again they have 2D distance in the horizontal axis of the virtual array. And finally, for the third transmitter, again we will have these 4 channels, and they are going to be located in the down right part here. Okay. So is everything clear so far? Okay. So now, so here we have seen how we can create the virtual antenna array, and in the radar platforms that we use, there are 2 ways of doing this. Okay. Actually, there are more than 2 ways, but we use mostly the 2 different ways. There's time division multiplexing, binary and binary phase modulation. There's also code division multiplexing and Doppler division multiplexing, but we haven't worked on those. So if I can have the time to like learn about those, I can give you information about it. And for the time division multiplexing, basically this is what we just described. We define 2 different chirps. So these blue and red uh, triangles are our first and second chirps. And in the first chirp, we are going to activate only the first transmitter. So in this case, we have only 2 transmitters. Okay, we don't have any elevation transmitter. So here we are in the first chirp, we are kind of using only the first antenna to transmit a pulse. And in the second chirp, we are using only the second antenna to transmit a pulse. So this becomes, so this chirp 1 and 2, this becomes a chirp loop. So in the millimeter wave studio that we are going to see, this chirp sequence is called chirp loop. Okay. And after finishing one chirp loop, we repeat it again, and we keep repeating it until our frame time is kind of full. Okay. So in the binary phase modulation, so in each chirp, we are using both of the transmitters. So we are using both of the transmitters, but there is 180-degree difference, phase difference between the 2 chirps. So how we are going to do it? So if you look at the dashed line here, okay, so this dashed line is the first chirp. So if you look at it, it's kind of use both transmitter 2 and transmitter 1, and it kind of has the coefficient of 1 because we don't have any phase information here. So this is the first chirp, okay? And in the second chirp, we have, again, we have transmitter 2, but we are multiplying our transmitter 1 with -1 because we want to add the phase difference, okay? So that's why we are multiplying this value with -1. And again, this becomes a 1 chirp loop. This 2 chirps becomes a chirp loop, and we keep repeating this. So now, in the data processing part, then we are decoding this data. So we have in this sample, so this is going to look like a 1 sample. In this sample, we have the data from both transmitters. So to be able to find this SA, this received signal, we need to divide it by 2 because we have information from 2 transmitters. And when we are kind of finding the data from the second chirp, we need to take difference of 2 chirps and then divide it by 2. In the code part, we are going to see how this is being done. But for now, conceptually, you can think of this as something like this. Okay. So in the in the like chirp configuration part in Wave Studio, there are certain steps that you need to do while kind of like setting this time division multiplexing and binary phase modulation steps. So this TDM is kind of easier I would recommend you to use probably this one. DPM is also, I mean, it's also easy, but sometimes if you forget to like adjust the phase, your data becomes corrupt, so you may run into problems. Also, you need to do like certain changes in the code part as well. So we'll see both of them, and you can use whatever you want. The only advantage of this binary phase modulation is that since it's using both transmitters for each chirp, it has higher signal to like noise ratio. You can get better kind of like stronger signals with the binary phase modulation method. Other than that, everything is the same as time division multiplexing. So now, when we were talking about chirps, chirps has certain specifications, as you said, like number of ABC samples you take, your slope rate, your chirp duration, etc. So those kind of things are being configured in a window called profile config in MMBase Studio. Maybe I should just open MMBase Studio and then show it to you. Okay. So first thing we need to do. Oh, okay. Oh, let's wait for it to open. So once you kind of like define these profile configurations, then you need to define your chirp configurations. So you need to define each chirp separately, like depending on how many chirps you are going to have, you need to kind of describe them. So in this case, for TBM, we need to define two chirps, and both of them are going to use the same profile, but one of them is going to be using first transmitter and the other one is going to be using the second transmitter. That's going to be the only difference in the chirp configuration tab. And next thing that we want to have is the frame configuration. So this will, did I start recording? I didn't start. Okay, let me start recording. Okay, it's recording. Okay. So now, in the frame configuration part, we need to create a subsequence of chirp one followed by a chirp two. So we need to create this chirp loop, and we need to repeat it and chirps divide by 2 times, because in each chirp loop we have 2 chirps. So number of chirp loops are going to be your total number of chirps divided by 2. Okay. And yeah, a frame is created by looping through this subsequence a specific number of times, you can say. And for the BPM part, we need to define a single profile, again, consisting of basic properties of the chirp. For chirp 0 and 1, again, we'll define 2 chirps, but each of them will kind of like use different phases. Chirp 0 is going to be programmed to transmit the phase of 0 on both TX1 and TX2. Chirp 1 is going to be programmed to transmit with phase of 0 on TX1 and 180 on TX2. So that's the difference. And the frame configuration part is the same. You need to create subsequence of chirp 1 followed by chirp 2, and then you need to repeat this for a certain number of times. So now you'll see some demo. But I have some like useful resources here that I highly recommend you to like look into this. Now I'll show them briefly to you. So the first one is FMCW Radar introduction slides provided by TI. So if I just open this up, so this has like 70 pages, but it's like slides, so it's kind of, you can read it very fast, and it kind of describes all the radar concepts, how the range is calculated, how the, actually I took most of my content from this slide. It also talks about hardware of the radar, like how the Fourier transforms are being applied, things like that, and how you calculate your range resolution, velocity resolution, and angle, resolution, everything. So what's your maximum range of your system? So you can find all the details in this slide. It's very useful actually. And the next thing is there is this introduction slide. This is kind of like shorter, but it's like an kind of summary of those slides. It has less information, I would say, but some of the things are easier to find in this article rather than looking into all the slides one by one. So you may find some of the things easier in this article. Yeah. And next thing is the video tutorials. These are kind of again provided by TI. So they have these video tutorials for the TI systems, and there are 50 videos. I didn't watch all of them, but some of them are very useful and essential, especially under the one under like this introduction to FMCW radar, range estimation, phase, velocity estimation. So these are kind of very useful, I believe. I would recommend you to look into these. Also, the one related to MMWave Studio is this one, sensor experiments, not experiments, sensor devices. So here this DCA 1000 training video. So in this video, basically, uh, they describe how you need to like set up your hardware to be able to collect data, how you need to connect your boards and like all the switches on the hardware are kind of like shown. What are the drivers that you need to like install to your computer, how they are going to look like in your device manager, and how you set up your IP address. You also need to change your IP address in your computer while connecting the Ethernet cable. Like it should be like this, like 192.168.33.30 and subnet mask of this. So these are very crucial. If you do not do those, you won't be able to collect data. The NVIDIA Studio is gonna throw error. And here you can watch some demo like how they are collecting data. And now I'll kind of like show you how it's being done. But I would also recommend you to look into this video. Now, other resource is the MMWave Studios user guide. So that video is also probably using this. So I'll kind of open it up. So this is a bit long, but it's kind of very useful, especially the part where you kind of like install the drivers. For example, yeah, you need to have MATLAB runtime engine in your computer. If you do not have it, you need to install it from here. The version should match with the MMWave Studios kind of requirements. So you can find installation steps here, and yeah, afterwards, like it shows you how you should kind of like see your hardware, how you connect it. So you also need to have this XDS emulation software package. So you need to download this for your computer. Depending on your operating system, you need to download the correct one. And you can just follow those installation steps if you are first time installing Studio to your computer. Now for the MIMO radar, the concepts about antenna configuration and kind of like how you should set up your chirps. You can look into this PDF file, and it kind of like shows you how BPM is kind of like how TDM and BPM are kind of being done. So time division multiplexing and binary phase modulation, they are kind of being explained in detail in this file. Also, one other thing is the radar capture with MMFC and ADC data format. So each radar platform comes with its own data format, depending on if you are dealing with AWR 12 something or IWR 16 something, 12 something, whatever the radar platform you are using, you need to check its DCA data format. If you process it in the wrong way, for example, if you collect data with 14 something, and if you try to process it as 16 something, your data will going to look corrupt. So you need to make sure that they are correct. And you can find this information in here. So they are kind of being explained in these tables. You can just read them and check them out, like how you are supposed to kind of decode your collected samples. So for each radar, there is kind of like certain differences. You need to be careful about this. And this is all about the conceptual things. Now I'll go into demo, but meeting is going to end in a minute. So I'll just stop sharing the screen and end the meeting, and I'll send you a new meeting link to kind of like show you the data recording with MMWave Studio. Okay, thank you for listening. Bye.